So hello, welcome back everyone. So this is probably the fourth video in this Navier Stokes series. So yeah, in the last video we wanted to find out, okay, which directions are positive for our stresses. So we needed to develop some vector conventions for our stresses so that we can, start our analysis on determining the net force on our body. Okay, so let's do it as per normal. We have our cube again. We have our cube again. And let's enlarge this to give it some more drawing space. Yeah, we have our cube again. And we have the delta x, delta y, and delta z. And we want to define some positive directions. Okay, so some rules of thumb. Firstly, for normal stresses. Now, what are normal stresses? Normal stresses are stresses that are perpendicular to the surface. So let's say the surface is this flat plane here. Normal stresses are stresses, the vector component of the stress, which are this way or this way. If you're talking about shear stresses will be this way or this way. And normal stresses, you usually denote them by sigma. And for shear stresses, you usually use the symbol tau. Okay, so for normal stresses. Okay, for normal stresses, if let's say you have the box here, you have a box here, and then you have this coordinate system, the simple xy coordinate system, xy Cartesian coordinates, the ones that we are most used to. Okay, so I'll have an x here and a y here. Alright, so it doesn't matter where that x and y is. You have to look at this box. Okay, you have to look at this box. So this, from the left to the right, is increasing x, from the bottom to the top is increasing y. And where are the shear stresses positive? Okay, this one is easy to remember. Oh, no, they're not shear stresses, normal stresses, sorry. The normal stresses are positive when they're pointing outside the box. Okay, so for any direction, well, we define stresses pointing outside of the box as positive. Okay, so let's write positive is pointing outside the box. Okay, let's write that down first. Sigma shear stresses, normal stresses, positive means outside the box. Positive means pointing out of the box. Alright. And, okay, what about shear stresses? Well, remember there are three directions. There's a shear stress in this direction, along this plane. And if you talk about 3D, there are shear stresses along this direction as well. Okay? You see this red arrow? This is along one direction, this is along the other direction on that plane. Okay, so shear stresses along this box again. How do we define positive? Well, if we have this y and x coordinate system, we draw the line y equals x. Okay, y equals x. Alright. So, if we have this line y equals x, we draw it parallel in the box. Okay? And where is the positive? Okay, the positive direction is that, well, if you're on this side, if you start on this line, whichever stress points you towards the line, that's y equals x, that will be the positive direction. So at the bottom, it will be this way, it's positive. Which I know is kind of weird, but that's the convention that's being used. So kind of get used to it. Alright, so you point it towards the y equals x, and then this is the positive direction. Alright, so let's write it down. Tau, which is shear stress, positive means pointing towards a line, well, y equals x. If you're talking about the xy plane, y equals x will be the line of reference. If you're talking about the zx plane, so instead of this being y, then this becomes, let's say, alright, I'm going to delete this. If this becomes z, the same idea. If you have a line z equals to x, this will be the line of reference, and you draw it across the box, and whichever direction is pointing towards that line, that is the positive one. Alright, now we have yet another problem that we must deal with, is that how are we supposed to name all these stress components? Because well, you see, each plane has 3 vector components of stress that can be acting on it. Alright? Okay, so let's write down naming conventions for stress. Okay, I'm just going to copy this over here so that there's a diagram of reference next time we look back. Okay, so naming conventions for stress. Now this is yet another a little bit of a headache, a small thing, kind of a headache, annoying thing that you have to learn. But don't worry, you only have to learn these things once in the derivation of Navier Stokes. After that, you kind of forget about it. You just deal with the equation. Okay? So let's go over naming conventions. Alright, so if you have a stress here, okay, I'm going to put it green color, and then you have a x and y plane, x and y plane, okay, and you have a normal stress in this direction. Okay, so what vector actually characterizes this plane? How can we name this plane? Is this an x plane or a y plane? Well, since this plane is actually perpendicular, it is perpendicular to the x direction. Okay, so we have to name planes first. Name the plane. So we have to look at what direction is it perpendicular to which direction. That will determine the name. So let's start with how to name planes. So before we start, name the planes. So we need to name the planes. We name planes by seeing what direction they are perpendicular to. Okay, so let's say this right hand side, this part, this plane I'm talking about here, this is a perpendicular to the x direction. So it's kind of a y and z kind of a plane, but it's perpendicular to the x plane. perpendicular to the x direction. Okay, so for shear stresses, this shear stress in particular is acting in the x direction and is acting on a plane perpendicular to the x direction. Simple? Okay, so x shear, this normal stress, normal stress. So this is the x direction. Okay, and then it acts on the plane perpendicular to x direction. Okay, perpendicular acts on the plane perpendicular to the x direction. So how do we name this stress? So this is what we call sigma xx. So it acts on the x plane. It is going in the x direction, and it acts on a plane perpendicular to the x direction. So sigma xx. And if you note the convention here, do you note the convention here? Any sigma will be, you see the letters that they refer to, any normal stress will be the same letter, because this is again in the x direction, acting on a plane perpendicular to the x direction. And then how do we name this stress then? How do we name this stress? This is acting in the y direction and is acting on a plane perpendicular to the y direction. So we call this sigma y. Same for here. Remember, pointing away from the box means positive for normal stresses. So this is also sigma y. Okay? And then the normal stresses are pretty easy because you see the letters are pretty much the same and they're pointing out of the box. But let's say you have shear stress. Shear stress is slightly more difficult. Alright, so again, let's have the x and y plane. This let's say this box here is in the x and y plane. So let's start afresh, new. It's on the x and y plane using this coordinate system here. And now we want to look at shear stress. So again, which side is positive? We need to draw our line here, the y equals x line. We draw the y equals x line, and we know the positive is the one that's pointing. Positive stresses are the ones pointing towards that line. Okay, so now, how do we name the stress? First, we need to know it is a normal stress. Shear stress, sorry. So shear stress are the ones that are parallel. They slide along the plane. This way. And that is tau. So what plane is it acting on? It is acting on a plane perpendicular to the x direction. So we have to write it like this. Tau x. Tau x, the first letter tells us which plane it's acting on. So this tells us that it's acting on the plane perpendicular to the x direction. And which way is it acting? It's acting in the y direction. So this stress is called tau xy. And if you talk about this plane, the positive is pointing towards the red line, the y equals x line, the y equals to x line. So how do we name this stress? This is also called, tau. Which plane is this perpendicular to? This is perpendicular to the x-axis, so it's tau x. Tau x. And which direction is it going? It's going along the y direction. Okay, so this is also tau xy. So let's go on the top. The positive direction is this way. It's pointing towards the line again. Obviously, this is a shear stress. Which direction is it? Which plane is it acting on? It's acting on a plane perpendicular to the y direction. And which way is it going? It's going this way. This is the x direction. So we call this stress tau yx. Okay? And how do we name this stress? Okay, so again, this is a shear stress. This is not a normal stress. This is a normal shear stress. Just kidding. Enough with the puns. Okay, it's a shear stress. I don't want to confuse you guys. I'm just joking down there with the puns. Anyway, so this is a shear stress. It is acting on a plane perpendicular to the y direction. So again, this is y. And then what is the direction is going? It's parallel to the x direction. So this is a shear stress acting on the y plane, or perpendicular to the y plane, shear stress acting on the plane perpendicular to the y direction, going in the x direction. So that's how we name stresses. So, okay, sigma, we already know sigma is for normal stresses. So sigma x means normal stress acting on plane x, or perpendicular to x, in x direction. Got it? Alright, so tau yx equals shear stress acting on plane perpendicular to y, and the stress is in the x direction. Okay, now we have gone through a lot of trouble just to learn how to name stresses. Now, why do we want to go through all the trouble again? So that we can find the vector components of the stresses that are acting on this little box of ours. Okay, so now let's do a x direction. Let's consider the x direction. X direction. Okay, then we can consider the y and the z direction, because momentum has a vector component. Again, it's a 3-direction thing. So let's just consider forces that are acting, forces and momentum in x direction. That's all we need to do for now. We can worry about the other directions later. So let me copy this over. And then we will stop shortly, but yeah, we'll have a short break. I'm going to delete this whole thing, or maybe not this whole thing. I like the box. The box is important. Okay, so I'm just gonna save this as control volume analysis. Oh, I can't save it here. I'll put it on the desktop then. Okay, so we are at 19 minutes. I won't drag this out too long. So we'll see you in the next video, and we'll continue our Navier Stokes equation. Thanks for watching.